All right, hello everyone. Today we are going to start our first lesson in Module 5, and we're going to start out with trying to just kind of understand what functions might be considered linear functions and what would not. So the homework that goes with this lesson is on pages 170 to 171. We're going to do 1 through 12 all, and then 14 through 20 even. So there's one thing we need to start out here at the beginning is a quick correction. This part is great. The graph of a linear function is a straight line. So officially in this chapter, we're only going to work with linear functions, which means when you are asked to do a graph, your point should come out in a straight line. Otherwise, you know you're doing something wrong. But this is the correction that needs to be made. I'm going to cross this out right here. They're saying that this is standard form of a linear function, and that is not true. Standard form, I'm going to go ahead and highlight here, and we're going to write out to the side the correct way to do standard form, which is ax plus by equals c. And so the rules for this is that the a and the b would both be non-zero numbers. So this might say like 3x plus 5y equals c, right? And c would just be a constant that doesn't have an x or a y after it. So this is what we were considered to be standard form. And a lot of the equations in this homework assignment are going to be written in standard form, and we're going to look at what to do with those later in order to make sure we can graph them. But then here are some other rules that are really important. In order to be in a linear function, there's some very important rules about the variables x and y. Okay, in order to be a linear function, your x and y have to have exponents of 1. So if you see anything that is an x squared or a y squared or a y to the third power, that is automatically not linear. The x and y are not multiplied together, and the x and y are not in denominators. The x and the y are not the exponents, and they are not in radical signs. So these would all be examples of things that are not linear. For example, right here, 2 plus 4 equals 6 doesn't even have an x or a y. X squared equals 9. This does not have an exponent of 1. It has an exponent of something greater than 1. So that is not linear. Right here, x and y are being multiplied together. Here, x is in the denominator. The x and y cannot be in the denominator. Right here, 2 to the y power. The y can't be used as an exponent. And then right here, the square root of y equals 5. That's the radical sign. A square root sign is a radical sign. If you have a variable inside of a radical sign, that is not a linear function. So a couple of the first homework questions that you guys see today are going to ask you to look at functions and tell, are these linear or not? So let's see if we can use these rules and figure this out. In number 1, if you look at where your variable is, this has a variable that is underneath a radical sign. Your x and y cannot be under a radical sign, so this is not linear. This one, 3xy equals 27. Okay, there's definitely a reason why this is not linear. Hopefully when you look at this list you see it. X and y can't be multiplied together. Not linear. Okay, this one, 14 equals 28 divided by x. Okay, right here where it says the x and y are not in the denominator, that's an x in the denominator, not linear. And then right here, 6x squared equals 12. Okay, x squared, it says right here that your x would have to have an exponent of 1. Anytime you have something where your exponent is something greater than 1, that is not linear. So these are perfect examples of what is not linear. Okay, and the good news is for you on your homework assignment, if you say that they're not linear, that means you don't have to graph them. But they're going to say, tell whether it's linear or not, and if it is linear, graph it. So we need to practice some now that are linear and make sure you're able to graph them. So we're going to skip over this part because this is not a specific skill you're going to have to do in your work today. So I'm going to go ahead and flip to the back to the extra notes. And so we want to make sure that you are prepared to actually graph linear functions. Because like I said, the homework will say, is this a linear function or not? If so, graph it. So if you get those that says, if so, graph it, and you need to graph it, here's what you're going to want to do. Since your equations are going to be written in standard form, you're going to want to solve for y. It just makes everything easier to work with. So then we're going to make a table. When you make your table, it's where you're going to make your xy table, and you're going to choose smart values to put in your x column. Okay, remember, think smarter, not harder. And then you're just going to solve for what y should equal. Okay, so here's the two examples we're going to practice. These two would be perfect examples of linear functions. 6x plus y equals 12. That's a linear function. It fits all of the rules that were on the front page. X plus 3y equals 9. That's a linear function. But this is what they mean by standard form. See, like ax plus by equals c. Ax plus by equals c. So what I'm telling you is it's going to be easier for you to get numbers to graph if you will make this say y equals an equation. So if you will solve for y, it's going to make everything easier. So I'm going to show you how to do that right now. Solve for y means get y by itself. Well, if you look how y is on the left side of the equal sign, the only other term over here is this 6x. You're going to make that entire term go away all in one step. You think to get rid of 6x, you would want to do minus 6x. Because guys, think about it. 6x, take away 6x, no more 6x. Okay, but the rules of equations still apply. If you're going to subtract 6x on this side, you have to subtract 6x on this side. So we want to write this as y equals. Okay, and then we're just going to get in the habit of this now because it's really good for when we do slope-intercept form later on. Get in the habit of whatever term has the x, put that in front and say negative 6x. And then put that positive 12 after it. And this is what I mean when I say solve for y. This right here. This is easier to work with than this when you go to try to graph this. Okay? So all I've done is get y by itself. Okay, and if you're asking yourself, why didn't I just do 12 minus 6 and put 6? Do you see how the 12 does not have an x, but the 6 does have an x? Those aren't like terms. They don't go together. You keep them separated. Okay, so now all we have to do is we're going to choose small intelligent numbers in our table. I would use -2, -1, 0, 1, and 2 almost all of the time. And we're going to plug those in and get answers. So you are welcome to do this in your head, on your calculator. If you need to write it out. But we're just going to plug these numbers in one by one. If I plug in a -2, -6 times -2 is 12. And 12 plus 12 is 24. If I plug in a -1, -6 times -1 is 6. 6 plus 12 is 18. If I plug in a 0, -6 times 0 is 0. 0 plus 12 is 12. If I plug in a 1, -6 times 1 is -6. -6 plus 12 is 6. And if I plug in a 2, -6 times 2 is -12. And -12 plus 12 is 0. And you will notice that these do consistently follow a pattern of going down by 6. It's kind of like that's our common difference when we did sequences. The -6 is going to happen every time. Okay? So when you go to graph this one, if you want to kind of think smart about how you set up your x and y axis, okay, you don't have any y values in the negatives. So we don't really need to do something that's going to go down to a super low value into the negatives. So I'm just going to do kind of an x and y axis, okay, that points up more than it does down. And on my x-axis I have -2, -1, 0, 1, and 2. Okay, and on my y-axis I'm going to do 6, 12, 18, and 24. Okay, graphing those real quick. -2, 24, -1, 18, 0, 12, 1, 6, 2, 0, And these are functions, not sequences. So we are going to connect those. It could include points in between there. It just happens to be that those are the 5 points we selected, but there are many others that could be included in this function. Okay, so let's try it one more time, mostly for the solving for y part on this example. If I want to solve for y, it means I want to get y by itself. So this time I have a 3 right in front of my y, and I have an x being added. Okay, so what you want to get in the habit of is it's just like solving a regular equation. You want to undo the adding or subtracting piece before you ever touch this multiplying or dividing piece. So the 3 that's in front of your y should be the last number that you move. So we want to focus on this term, the x. To make that x go away, I would subtract x. X minus x. Gone. But if I do that on the left side, I have to do that on the right side. So here's what my equation says right now. It says 3y on the left side of the equal sign. And then this I would write as negative x plus 9. Okay, and then the last step for getting y by itself is this currently says 3 times y, so we know that the opposite of multiplying by 3 is dividing by 3. But here's the catch. Now that we need to graph this, I need you to think of this as dividing each term by 3 instead of just putting one big 3 across the bottom. So here's what we have. We have y equals by itself, which is good. We need to talk about this. It's as if there is a negative 1 in front of that x, you guys. So in other words, this is negative 1/3 x, but then 9 divided by 3 is 3. So this is how we solve for y, and this is what's going to make it easiest for us to create a table to graph. Okay, now we want to think back to being smart about the numbers we put in our table. When you have a fraction, you want to look at your denominator, and in your table, instead of using the numbers we used previously, you want to use multiples of 3. So I'm going to use -6, -3, 0, 3, and 6, because this is going to give me nice numbers to work with here. So again, you're welcome to write this out if it helps you out to understand. But guys, -1/3 times -6 is 2. And 2 plus 3 is 5. So you guys can talk that out if you need to. Plug in a -3. -1/3 times -3 is 1. And 1 plus 3 is 4. If I plug in a 0, -1/3 times 0 is 0. So then I add 3 and get 3. And by now you should see a pattern. But -1/3 times 3 is -1. -1 plus 3 is 2. -1/3 times 6 is -2. And -2 plus 3 is 1. So this is what I am going to graph. So because I went from -6 to 6, this graph needs to be a little bit wider from left to right, but it doesn't have to go up super far. So I'm going to make it kind of wide. So I'm going to have to go out on the left and right sides to 6 and -6. And then I need to go up to at least 5. That. And I'm going to graph my points. -6, 5, -3, 4, 0, 3, 3, 2, 6, 1. And we are connecting on a function. Okay, so the good news is you won't have to graph each of them. You will just have to be able to look and see, is this linear or not? If you say yes, it's linear, you have to graph it. If you say no, it's not linear, you do not have to graph it. All right, I'm going to move on. We need to add a section in here about modeling with linear functions, which usually when they say modeling, they mean word problems. So we need to be able to look at a word problem, create a graph, decide whether it should be continuous or discrete, And then we need a reminder on how to do domain and range. So the first problem we're going to look at for this together is off of page 169 in your book, and it's the number 10 problem that says your turn. So take a second and get to that, and here is what it looks like. So Christoph rents a kiosk in the mall to open an umbrella stand. He pays $6 to the mall owner for each umbrella he sells. The amount Christoph pays is given by f of x equals 6x, where x is the number of umbrellas sold. Graph the function and give its domain and range. So your function is right here. They want us to graph it and give the domain and range. So we're going to take a look at this. Here's the function. Okay, and then you want to make sure when you're graphing something like this, you're clear about what's going where. They told you in the problem that x stood for the number of umbrellas sold. So I'm going to go ahead and write down here on the x-axis, umbrellas sold. Okay. And then if you think about what that's going to affect, the more umbrellas he sold, okay, this isn't talking about his profit, what he's going to make. That 6 says he paid $6 to the mall owner. So I'm going to say this is the amount paid in dollars. And I want you to think for a second before you even start. Some of the word problems aren't going to ask you to even graph. Before you even have to graph it, they're just going to ask you, would this be a continuous or discrete situation? So I want you to ask yourself about your x right here. We're talking about umbrellas sold. Have you ever known anyone to sell part of an umbrella? I'm going to hope you just said no. So if we can't sell parts of umbrellas, we would never have any points that would be connected in between. So this is automatically going to need to be a discrete graph. And let's just kind of think about what would happen in this story if we started selling umbrellas. For one umbrella, he's going to pay the mall owner $6. For 2 umbrellas, $12. For 3 umbrellas, he's going to pay $18, and so on. So let's be smart here and just count. 6, 18, or sorry, 6, 12, 18, 24, 30, 36. Sorry if I said my numbers wrong a second ago. 6, 12, 18, $6 per umbrella. So this would look like this. Discrete graph with no points connected, like this. So we've graphed it. We understand it should be discrete. So let's think about domain and range from previous units here. When you're going to write domain for a discrete function, you would list the individual numbers. Okay? So what I want you guys to think about here is if the guy sold 0 umbrellas, he would make $0. So I'm going to choose not to include 0 in this. He could sell 1, 2, 3, 4, and so on, and I'm just going to put ... This is how they're wanting you to write your domain. Okay, range for this would be amount of money paid. So 6, 12, 18, 24, ... So for domain and range on discrete, they're wanting this list. And since he could sell who knows how many umbrellas, you don't need to continue to go on forever. You would just put the dots to indicate you understand this could keep going. But let's look at a different situation when it might not be a discrete problem. Okay, if you look at example B off of that same page earlier up here at the top of page 169. I know they've already graphed it for us, but this is a good example of one that's not discrete. It says Elsa rents a booth in her grandfather's mall to open an ice cream stand. She pays $1 to her grandfather for each hour of operation. The amount Elsa pays each hour is given by f of x equals x, where x is the number of hours that her booth is open. So she's getting a good deal, I'm thinking, because it's her grandpa. Because if it says x is the number of hours and f of x equals x, it's basically saying the number of hours literally equals the amount that she's going to pay him, because she pays him $1 an hour. Okay? So in this case, okay, x is your number of hours. So I'm just going to put 1, 2, 3, 4, 5 down there. Okay, and then this is the amount of money that she pays her grandpa. Okay, and this again doesn't need to go, just 1, 2, 3, 4, 5 would be fine, because this is a real basic situation. It's for 1 hour, she pays him $1, 2 hours, $2, 3 hours, $3, 4 hours, $4, and so on. Okay, but in this case, if you're thinking about this, would it be possible for her to be open for part of an hour instead of a full hour on the dot? I would say yes. Like, she could definitely be open for partial amounts of time, like a half hour closing, at a time or something like that. So this would be one where I would say we would want to call it continuous. And so I want to remind you that domain and range look different for continuous functions. And I'm going to teach you a cool symbol that we didn't learn before. Okay, for on these domain and range, guys, keep in mind she might not even be open a full hour. So this could start at 0, like she could be open for maybe a half hour in there somewhere and pay him 50 cents. I mean, that's a little odd, but it could happen. So we would say in this case that the domain could really be any numbers that would be greater than or equal to 0. So in other words, we're saying all real numbers greater than or equal to 0. So I want to introduce you to this cool little symbol. Kind of looks like a capital R with 2 legs. And that little symbol stands for all real numbers greater than or equal to 0. Okay, and we could say the same thing for range, because depending on how long she's open, she could pay him anywhere in between $1, $2, $3, $4, $5, somewhere in between there. So her range could also be all real numbers greater than or equal to 0. So you might want to make yourself a note that says all real numbers is what that stands for, because that's a new symbol for us. And that's how they're wanting you to write domain and range on these continuous functions here today. So taking a look real quick at what your homework is, let's make sure we're super clear on directions. Your homework starts on page 170 and you're doing 1 through 12. Okay, look at the first 6. Determine if the equation is linear. If so, graph the function. So you're going to look at this and say, okay, yep, number 1, that's linear. Okay, then graph it. But number 2, no, that's not linear. Then don't. When you get to 7 through 12, look at this. State whether each function is discrete or continuous. So you don't have to graph it at all. It's just where you have to think about, like we did with the umbrellas. Are you going to buy part of an umbrella? No, that's discrete. Okay, but like the girl who was renting the ice cream stand, could she be open for part of an hour instead of a full hour? Yes. That's continuous. So you're not graphing or working anything out. You're just deciding discrete or continuous. 14 through 20, you're going to do evens. So these say graph each function and give its domain and range. So these are like your word problems where you should be deciding what style of graph to do and write the domain and the range appropriately. 18, state whether each equation is in standard form. So look at that front page of your notes and decide whether these are in standard form or not. And then 20, they've already graphed it for you. You just need to answer a couple of easy questions at the end. So hopefully this helps out and we all understand lesson 5.1.